Next few minutes, I'm uploading the last one I just recorded. Been a few minutes. The timeline of that history effectively is such as if you design and build this and manufacture this CPU, you have the ability to start affecting things, and then you realize that you have the ability to effectively see what is not what it should be, because you can calculate quite a shit ton, and it basically means you have a detector that's interacting with the CPU. That means that you then have the ability to see what and the reasons why it is not interacting appropriately. Because you can then start calculating further and further and further degree increments out and start to see that there are things that are there that are not a part of our reality. And if you do it with your brain, though, which that one's a wait, what? And I have to give you a caveat. Wait a second. Here's how our brains work. Let's take a bunch of fiber optic, little tiny nano to micro wires. We're going to design a bunch of detectors for the various gamma ray to radio wave detecting for that fiber optics that has a bunch of series of lenses that effectively help start the process of interaction and amplitudation, which is not a real word, but I suppose I can use that word even though it's not a word. Point is, they amplify the amount of photons released for those given wavelengths, photons, that is. So if you do that correctly, layer it correctly, you have the ability to then, along with electricity, to help basically modulate and increase with either fields and or the material itself the amount of photons, or if not the amount of photons, make sure they're not going to fuck around by polarizational means and methods as the lens and the photons are interacted with. Now, as a result of, it's like, how does that radio wave? Well, I talked about it in my Twitch Xenon Reality, but there's these few crystals where it's like, if you happen to start to try and interact it, then you know about this distance before it starts to, because it's going to be tilted this amount. Or divoted, whatever it is. That's the lens part. But if that given wavelength, the radio wave, microwave, all of that, then you can then simply make sure to hit it at exactly that angle every time and curve it far greater and far shorter distances. As a result of that, you can then build a detector in a smaller area that runs with the fiber optics for those given wavelengths, because that's all you have to do to make that work. Now, as those detectors go into every single one of those detectors for every single wavelength sector, and then every single given frequency down to whatever hertz accuracy that you want, you then can shove it into an analog. This is all a bunch of ones and zeros and everything else, because it's pulse and then, but an analog means I can create a circuitry design for every single one of those things. But then it means I can amplify, send it off, and it is encoded as a 1 or a 0 for this frequency, or the 101, whatever. Remember, because I know now about the breakout thing, I don't have to have it be anything other than that pulse. I don't have to need to have it to be a bunch of ones and zeros. I don't. You only need it to be the 1 or 0. It did do that, or it didn't do that. It did it for this long, it didn't do it for any longer. That's the circuit design. This is the programming that helps the circuit design work for analog. You're going to have to shut the fuck up and listen for a second. What that means is this analog design. I'm going to get out of here. He's swearing. Be quiet. Listen. This means that circuit design for an analog can go straight into a RAM that I'm going to break into and design it so that way that 1 and 0 is going to go up, side, and in. So from inside and out. Okay, like it's going to basically just fill all the rows and all the little, vertical space with the 1 and 0 respectively for what it is doing. I'm going to have another analog that's going to go, okay, so my thing is I'm timed to basically, once it starts going, with error correcting memory, I have to have that basically know what that is. And so like I have to wait for it to check and then send it. You have to do that. But like that's because it's like it needs to be in a box that's full speed for very, 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 very high speeds. Because this is a design that's like our eyes. This is how our eyes work. Right? Just give it a second. Because we know this is a 1 or a 0 and for how long and how little it was going for, then the programming turns into, okay, I'm going to take that information and basically delete it the moment I detect it. I'm going to suck it out. That is the information in my circuit. That means I can grab that information as necessary and immediately delete it and give it now space to immediately start filling again. So it goes up and it doesn't need to know where the space is because it's going to delete it as it goes. And so it just needs to be timed appropriately to follow back and out and in. So as I delete it, it's going out and in and up and down. And that's the patterns of the fill and delete and read. That's read. Now, we're going to use that computer to basically turn it into a series of categorizations and specificities. So this is this wavelength. This is this amount of data for that specificity. And then this is how much it happened to have. That can then be sent off to a computer that is pretty much going to do the same thing with logic gates. It's going to suck it in. We need fiber optics. I was like 8 terabytes a second would be easy. In fact, I would fill it up that fast. So I'm going to freaking go through, grab that information, 8 terabytes a second. I'm going to fill it up with the big old chunksters of server CPUs. I mean chunksters, because I'm like, hey, shh. You dummy dums. I don't care what you specify. I can write you my code to go, that fucking CPU on the machine and binary code says, no. This core is for 2 terabytes. This core is for 2 terabytes. This core is for 2 terabytes. Because I only want the byte and bit information. I already know what it's going to be. I mean that. So give me a second. So everything I'm going to fucking break into and essentially recode it. Instead of like constantly sending like only through the fucking stupid line the direct current style of increase of electrons. No. We're going to go back to that whole Hertz rate style of like sending and that means like a bump suddenly gets registered instead, because that's how they can detect it, is now actually a registered 1 or 0. Respectively. And because we can use the same techniques for those RAMs, and they have 8 channels, and I have all of the, and I'm like, wait, I need 2 terabytes, no, I need 512 terabytes. This thing's going to go through 8 terabytes a second. I need 512 terabytes for 2 CPUs each. These are big chunkster 64-thread CPUs, 512 terabytes each. They're going to brute force this sucker, and that's my capacitor effectively. That's going to store it as a brute force. Each one of the caches already has knowledge of where it's going to be on the RAM, when it's going to be there, what it's meaning, and everything else. That's the programming for that. It goes to this CPU, logic gate, this logic, blah, 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 is going to be a 1 or a 0. So I only need to know that. It's going to send it immediately to that and make sure it puts out the right 1 and 0 for those categories, because it knows how it's going to send it into the RAM ahead of time. That's how the program works. Now, because of this, I can really massively increase bandwidth and throughput of my CPUs. The interconnect, 30 terabyte a second, that's my cache, along with the other cache, and then the other cache, and then the very, very last cache, which actually there's 4 cache levels, but that cache big boy level is also the interconnect, which I need to know about the timing for that, but the point is, it knows. All right. Now, that can also have its own version of that flipped, 1 and 0. Now it's going to go to the controller to 700 terabytes of hard storage. Because I need that to be sent over to the other 2 CPUs that are just going to hit 8 terabytes a second of basically that's sent over to there. This is ingestion. Like ingestion, and like we're not doing any calculations. It's just to be able to handle the damn shit. It's literally all it's for. I'm not even kidding. It is to send it to the calculators, which we're really going to do. Because it's like, really, realistically, I need that to know where it's going to go. Ooh, yeah, there we go. Now, these hard drives are expensive. All of it's expensive. What I just described is expensive. Okay? But, bear with me. That design needs to know, because it's like, look, I can fucking do that with my controllers on those hard drives. This is now the new controller. This CPU is the controller. I know where it is roughly because the program knows from that controller where it is all. And they're going to basically use a series of gigabytes of data, or a terabyte, whatever, inside of those hard drives. And we're talking NVMe flash. We need fast. So, what that means is that's now the new analog. So this is the controller. I already know where it's going to go. This is going to send it off to the various data points in the rows and height and so on. And because it already knows what that data is, I just need to know it's going to the right place. So I'm going to fucking effectively send all of it into one ginormous flash. And I want it to all know what the stored information is going to mean for the other 2 CPUs to basically get it and then know what it is and then be able to use that for calculations. So it's even faster. But hold on, because I'm sending it even faster to that because it's going to fill it up. But because a 0 is already known as a 0, I can fill that 0 up. And then I'm deleting it as I go through onto the other 2 that are going to calculate with the other 512 terabytes for each of those. Which is like 512, they don't make those. You can specially make these, and you need a special controller anyways for the damn RAM. And the ECC is no longer anything other than a cache that knows where the information is and what the information is, so the CPU doesn't have to do anything other than send it to the correct logic gates. That's what the program does. Just throwing that out there. If you didn't know how to, like, conceptualize this pickup speed. So, what this means is that now knows where the information is, what all that, and it knows ahead of time on the other side of these other 2 CPUs, 64 threads each, with big data, big amounts of data, for very, very, very large amounts of continuous frames. Because each one of that analog is going to be like, this is this is. Now, the categories means this is all the same frame. Now, this is this frame with this specificity of frequency, and then this amount of data for how high, how low, its direction, spin, travel, all that, from its angle and everything else, and in relation to all the other different little tiny pixels of those fiber optics. So you have an incredibly high resolution, which you can tailor around. Give me a second. Now that's going to go into your cache, effectively, basically, but it's hard drive. That's your hard drive. That's what your brain does, okay? That's your hard drive. All right? Now that is then going to get sent to your CPU. That CPU is just going to know what it is already. We've already figured out what the CPU, or what the data is. We just want it to be stored as fast as possible, because we're going to go 8 terabytes a second, and you need to store it. And you need to be able to store it quickly. So, that means those hard drives are extremely, really fucking brutalized. The RAM is brutalized, the CPUs are brutalized, the hard drives are brutalized, everything's brutalized. It is maxed throughput bandwidth. It would never be able to do that off of regular code. You can't do it like that. You have to code it like this. Otherwise, it doesn't work. Your bullshit byte information, this is bits, and it's going to specific logic gates that you need to have for machine code, your motherboard code, all of it. You need to literally manhandle, mangle their code, get rid of it. We're doing this. And you have to order special RAM. You do have to do this. But you could do it. Now, what that means is that is getting deleted, same kind of style as the RAM. As we're reading it, it is deleting it. And we're freeing up space, and so we have the ability to add multiples. Now that pin data that's going over, and like we're going to basically do that little frequency line, we need multiple frequency lines for multiple different voltages, for multiple different increases and decreases. And oh, wait, I haven't even gotten to the best part. That CPU, you remember this? Because we have a capacitor and it, like, we have a hertz rate. What is this hertz rate? Fucking get out of here. I don't want a hertz rate. I want a completed circuit. So I'm going to divot and then increase. So that way there is never not a always direct current going through it. I have to change that. Now, the reason why is because I have to change how it is those ones and zeros are interpreted to be ones and zeros down the line. I have the code for that. Now, that's not increasing clock rate. It's just making it a completed circuit that then flows it through and gives me the correct ones and zeros to the pins that then does it again to your controllers, to your hard drive, which increases maximum bandwidth and throughput. Big boy stuff. We don't want small boy stuff. We want big boy stuff. Or person, whatever. I don't care. Point is, it's much faster because I know what the 1 and 0 is going to be. I know how to time it to the pin that is going to be the correct series of datas of 1s and 0s, which is all going to be able to be interpreted by the other two sets of computers. Now we're finally there. These things normally would never be able to handle that kind of 8 terabytes a second at all. I don't care what anyone says about the controller, blah, blah, but it doesn't matter. I've got bandwidth for 700 terabytes of these NVMe flash drive storages that are going to use all of that and delete it as it's getting brought in. And I mean delete it. So now it goes to the 512. Now we know where it is. Now that's a real, like, this is a big boy storage, the basically like a big old funnel that we're now going to funnel into these calculated. Now, that means we're going to compile all these frames to mean all of these different frequencies to all of these specificities. We're going to compress that data, and then we're going to send it essentially to the next series of fiber optics. That's right. So instead of, like, let's say it was 8 terabytes, we're going to compress it to 4. Basically. About 4 terabytes. Compress, and we already know what that is. On the other side of the other, where it's going to go to the real servers that are really going to fucking do the calculations. So that is then going to get sent, 4 to 6, because it's really a lot of data. And so, you know, really it's like actually like a couple frames might be separated, but they'll be tagged as each one of these frames. To one frame is actually all of that packet of data. Really depends. Like, remember, you have to go through multiple logic gates to do that instead of just sending it through one. So it takes longer degrees of time. And so, like, that capacitor, that is the hard drives, and then the other hard drive capacitor, which is, the 124 terabytes, petabyte of RAM, and then it's the cache and everything. And so it's like, actually, while we can theoretically do it for a while, for a burst, not all the time, and certainly you are going to have to give up the amount of calculations that you can do eventually once it's full, and it'll recognize once it's full, and it's like, back to the 6 terabytes. But we are going to hit that 8 terabytes onto the switch, and we have to compile and break into that data, and we have to basically make sure everything's known, because we need to really increase throughput and data transfer. You know what I mean? Almost done. Give me 1 second.